What's up, guys? Chapter 5, single phase mass balancing. Essentially, in this problem 54, we're going to see a mass balance with equilibrium using ideal gases. So the first thing I want you to do is to see this flowchart or diagram. It's the production of methanol, and it's done by a feed. Then you get the recycled feed enters the reactor, then the product goes to a separator. The separator divides probably methanol, and then the gases go to the separator number 2. Then we send some recycle, and F is our purge gas or outlet gas. So let's read each one of these. The following specifications are given. Stream A, fresh feed. It's a mixture of carbon monoxide, hydrogen, nitrogen, and CO2. What else? Letter B, which will be after the mixture. B is feed to the reactor at 30% mole carbon monoxide, 63% hydrogen gas, 2% nitrogen gas, and 5% carbon monoxide, dioxide. Now the reactor, which is this, the reactor occur two reactions. The two are at equilibrium at 200 Celsius and 4,925 kilopascals absolute. So essentially we have the carbon monoxide will react with 2 moles of hydrogen to form the methanol, and the carbon dioxide will form with 3 moles of hydrogen to form this methanol and water. So essentially we are forming methanol in both reactions. They give us this constant of equilibrium. I think at this temperature, and yeah, you can operate it. And what else? C is the reactor. Let me go a little bit up. C is the reactor effluent, essentially the reactor outlet. Contains all the feed and product species at the reactor temperature and pressure. Species partial pressure satisfy the two given equations. So they tell you that reaction 1 and reaction 2 actually apply and respect the theory. Separator number 1 condenses all methanol and water in reactor effluent. So this is all methanol and water. Probably letter E. Well, as I said, letter D is liquid methanol and water. Now letter E has gas containing nitrogen and all the unreacted substances, which is carbon monoxide, hydrogen, and carbon dioxide, which are our raw materials. So probably you want to separate them and get them back into the recycle. Now separator number 2, it's a multiple unit separation process. We're going to essentially split it in G and F. What is F? All of the nitrogen and some of the hydrogen stream E, which makes sense because hydrogen and nitrogen are the most difficult to condense or to reuse. Letter G, it's recycled stream, it's CO, CO2, and 10% of the hydrogen used in the feed in separator number 2. So we have here a relationship. Now they tell you taking 100 kilomole per hour of stream in B, so it's essentially this 100 kilomole per hour in the stream. Calculate the molar flow rates and molar composition of the remaining 6 labels. So that's a lot. We need to find A, C, D, E, G, F. And not only that, we need to find flows and composition. So let's do it. Let me show you the strategy I'm going to use. First of all, we're going to do our flow chart or flow diagram. Then we're going to try to use all the information and start doing our mass balancing. We're going to start with the extent of reaction in the reactor. We're going to analyze, or let's say do our mass balance here. Then we're going to substitute in the equilibrium data in K1 and K2. Before that we need to find our molar compositions given epsilon, then given the molar compositions, then we substitute in K1, K2. Solving shall give you the extent of reaction in 1 and the extent of reaction in number 2. Having these extent of reactions, we can continue and solve for all the molar flows in the reactor, outlets and inlets. And once we have these smaller flows, let's use mass balancing to find the other moles, let's say J, in the process, which is essentially by mass balancing. It's not that difficult. I think the most difficult part will be finding the expression for K and solving for epsilon, or the extent of reaction. So let's go and do what we just told you, and let's do the diagram. I'm going to do the diagram here. It's something like this, N6, N7, N8. Get mixture here. This is the inlet, this is the reactor, this is the first separator. Well, let me give it a little bit more space. This is separator, it goes up to another separator, and we take this and we get back with the recycle stream here, with the recycle stream here, and we have this here is our methanol and water. This is essentially the N1. Well, the molar flow here, it's 100 as basis. We have these relationships or these compositions. So let's draw them. CO2, nitrogen, hydrogen, carbon monoxide. This is the reactor. Yeah, you know here it's CO, and N3 is, sorry, N2, it's the hydrogen here. And what else do we need to add? Oh yeah, all the outlet, 1, N2, N3, N4, and N5, and of course the moles. I'm going to directly put 2 moles of nitrate. I don't want to add variables, but you could use N6. I already used it, but you can use another flow to state the molar flow of nitrogen going out. But since it is inert, I'm going just to add it here. Carbon monoxide, hydrogen, of course, CO2. This is the outlet gas. They don't react completely, and of course the methanol that's being formed, and water. This is exactly the same N4, and this is exactly the same N5, since we are taking it out completely. And at the outlet, it's kind of tricky. It's the 2 kilomoles or 2 moles of nitrogen I told you that are inert. They go here. You have N1, N2, and N3, and it's, since the 10% is being covered in the recycle, the 90% must be going out. So let's write this. And yes, essentially we're done with the mass balancing diagram. We still need to solve for all these, N1, 2, 3, 4, and 5, and 6, and 7, and 8, and we're done, guys, because all these other flows are dependent of N1, N2, N3, whatever. So we need to find all these, N2, 3, 4, 5. It's kind of easy because they tell you they're separating completely this, so you don't have to add a relationship of separation, coefficient, or whatever. Just simply add M4 goes here, M5 goes here, 90% goes here, 10% goes here, and it essentially is everything, guys. So let's start with the extent of reaction. We already got our flow diagram. Let's start with extent of reaction. Good. Hopefully you remember the definition of extent of reaction, which is, where is it? Well, let me write. Eventually I'm going to need to write the the reactions, but let's wait for it. N of 1 is the initial moles of species I plus beta or nu value and extent of reaction 1 plus the value extent of reaction 2. So good, we have this equation. Let's start solving. Let me write the equation very fast. Carbon monoxide plus hydrogen, 2 hydrogen gas are in equilibrium to form methanol, and CO2 plus 3H2 in equilibrium to form methanol and water. So let's start doing this, guys. I'm going to draw the new table so you're not that confused. Something about C, yeah, here. So CO, H2, CO2, and methanol and water. Reaction number 1 and reaction number 2. So carbon monoxide is -1 in here, and here we have no CO. This is -2 and this is -3, guys, so take care. CO2 it's a reactant, -1, and we don't have any, no sorry, we have anything, or we have nothing in reaction number 1, and we have 1 here. Methanol is being produced in both, +1, and water doesn't make sense in reaction number 1, and we are producing 1 mole of water. So let's substitute everything here. Initial amount of moles, hopefully you know it. If not, don't worry, just wait for it. And of CO2, and of methanol, and of H2O, and of nitrogen. So the initial amount of NCO will be all this. We have all these values, which is 30 moles of CO, 63 moles of hydrogen, 2 moles of nitrogen, and 5 moles of CO2. So carbon monoxide initial amount is 30, hydrogen is 63, CO2 will be 5, methanol of course it's 0 because it's a product, and water also 0. What else do we have? Nitrogen is 2. So let's add our extent of reactions. Let's start with equation number 1, reaction number 1, which is this column here. We need to, okay, we have -1, epsilon 1, H2 is -2, epsilon 1, CO2 makes no sense, so let's just add 0. Methanol is +1, epsilon 1, and water makes no sense, so let's add 0, and nitrogen, it's an inert, it's always 0. Let's start with reaction number 2. CO makes no sense, so let's add 0. Hydrogen, it's -3, epsilon 2. CO2 will be -1, epsilon 2. Methanol here will be simply +1, epsilon 2. And water will be here also +1, epsilon 2. So also makes no sense here. So let's add all this to get the total amount of moles. Total amount of moles is the addition of all the moles. I got 100, which makes a lot of sense because we are adding 100 moles to the reactor here. So that's cool. And now we add our extensive reactions. -1, +1. Okay, this cancels with it, and you get -2, epsilon 1, and -3, -1, -4, -2, -2, epsilon 2. Okay, so let's number these equations. 1, 2, 3, 4, 5, 6, 7, 8, 9. Actually, I'm going to, this one is going to be a special one, alpha. You're going to see why later. So we are done with our extended reaction. Let's do some mass balancing to find the definition of I, which is the amount of moles of I divided by the total amount of moles. And the total amount of moles, we're going to see that I'm going to use alpha because I don't want to write a lot. So it's usually good to just substitute this, because if you make a mistake because you're writing the same thing over and over and over, you will not like it, and probably when you want to check your errors or mistakes, you will not be able to catch them easily. So yeah, let's substitute for hydrogen, no, carbon monoxide, which is A of CO would be the amount of moles of carbon dioxide, which is, let me just substitute this. It's number 3 divided by alpha. Y of H2, it's 4 divided by alpha. Y of CO2, it's 5 divided by alpha. Y of methanol, it's 6 divided by alpha. And Y of water, it's 7 divided by alpha. And I don't have space, but Y of nitrogen, it's 8 divided by alpha. So I don't want to substitute right now, so technically we have this, you just need to substitute. Let's go find an expression for K1 and K2. So remembering, hopefully you get P1 was partial pressure of methanol divided by partial pressure of CO and partial pressure of H2 to the second power. Just check that. Okay, yeah, perfect. And the second one, Kp2, it's partial pressure of methanol, partial pressure of water, partial pressure of CO2, and partial pressure of hydrogen to the third power. And we know these values are constants, so let me add that constant. It's 3.49. 3.49 to the minus 5 power, I think. No, minus 6 power. And the Kp2, it's 5.19 to the minus 8. So let's start. Let's do this. Partial pressures, remember partial pressures are just partial pressure of I, it's Yi times total pressure. So essentially we just need to multiply this by P. So partial pressure of methanol will be, where's Y methanol? Here. It's 6 divided by alpha times pressure. Partial pressure of CO, it's here, it's 3, equation number 3 divided by alpha. And P, this one here, partial pressure of hydrogen, where is it? Hydrogen here, 4 divided by alpha. You need to multiply by pressure. All these by pressure, and all these to the second power. Let me do some math. Pressure goes with pressure, alpha with alpha, and you get 6 divided by 3, and 4 to the second power, and alpha to the second power, and pressure to the second power. So let me put it a little bit nicer. Probably you think this is strange. Yes, it is. This is no normal notations, but I do it so you can later substitute. So this is Kp1. Let's find Kp2. Kp2, it's partial pressure of methanol, which is 6 divided by alpha times pressure. Now pressure of water, which is, where is it, 7 and alpha times pressure, divided by PCO2, which is 5 divided by alpha times P. And the next one is tricky because it's to the third power. So hydrogen, once again, it's 4 divided by alpha by pressure to the third power. So cancelling, this one goes with this one cancels with this, and you get 6 alpha pressure divided by 5, that multiplies 4 to the third power, alpha to the third power, and pressure to the third power. Still cancelling a little bit more. One pressure goes with second pressure, and this one we can send it up, so it's 6. No, actually we need to cancel. This one goes with this, and you get to the second power, and alpha to the second power. This is just some algebra. Hope you are not distracting that much. So you get this, guys, perfectly. Yes. Hopefully you don't mix it a lot, but this is, let me tell, this is equation number 10 and 11. What's next? We have our equations. Now we need to solve for epsilon 1 and epsilon 2, and as you see, 6, 3, 4, and 5 depend on epsilon 1 and epsilon 2. Alpha depends also in epsilon 1 and epsilon 2. And pressure, it's a constant, so we can solve it. I solve it in software, so I'm not going to show you how I solve it, I just solve it. Hopefully you can solve it too, it's not that difficult. And you will get the epsilon 1. And of course, remember there's a constant here and the constant of kp2. So this is actually an equation. Let's see, constant 1, and this is constant 2. So solving, you get 25.3, and epsilon 2 will be 0.0157. So you can see there's a lot more happening in the first equation than in the second equation. Now let's substitute epsilon 1 and epsilon 2 in equations I think 3, 2, 9, and alpha, which are, let me show you which ones are here. 3 to 8, sorry. 3 to 8. And we don't need alpha because we're calculating moles, so we're going to substitute in the equation that gives us directly moles. We don't need the mole fraction. So N1 equals 30 minus 25.3, 4.7 moles of CO, kilomole of CO per hour. And 2, which is essentially hydrogen, it's 63 minus 2 times the extent of reaction, minus 3 times the extent of reaction number 2, you get 12.4 kilomole of hydrogen per hour. Flow mole 3, it's 5 minus 0.01. Extent of reaction 1, it's here. It's almost nothing. Let me just tell you which one is CO2. And 4, it's 25.3 plus the extent of reaction will give you 25.3. It's almost nothing, so okay, you could leave it as it is. Kilomole of CO2, I think it's water. What is the CO2 methanol? It's right there, water. Yeah, it's methanol per hour, and then water will be essentially just the formation of our extent of reaction number 2. Kilomole of water per hour, and finally the nitrogen, which is very, very easy. It's, where is it? 5 Oh, well, we didn't actually use it, so let's just, we are defining as nitrogen, so it's 2 mole kilomole of nitrogen per hour. Now adding all this will give you the total amount of moles, which is about 49.4 kilomole per hour. Let me just double check. Yeah, perfect. So we have all the outlet. This is only outlet of the reactor. Don't think we have all the mass balance. This is only these guys. We are still need to look for the other mass balancings. Why not? Let's calculate the composition, smaller composition. Y of I, it's N of I and T. So FCO, it's, yeah, CO, Y of hydrogen, Y of CO2, Y of methanol, Y of water, Y of nitrogen. This is essentially moles of, we have 4.7, 12.4, we just calculated. I'm just rewriting all this. And divide everything by the total amount, which is 49.4. And calculate all these. You get these values here. This can 26, I think. Yeah. And this is like 1%, I think. But no, but actually it's a little bit more, it's 4%. And if you add everything, it should add to 1.0 or something about that. So good. Probably if I were a teacher, I will give you half a point because you are almost half there. Now, sorry about the movement, we got this in the reactor. Now we need to do mass balancing to get all the other compositions. So yeah, let's do it. Mass balancing in process. So just to take you a look, we got almost everything. We got N1 and N2, so this is already calculated. And we got all these too. We just need to find N6 and N7 and N8. I mean, we have N1 and N2, so we just need to do the numbering, N1, N2, N3, and N4 and 5. It's not that we are done, but essentially, mathematically, we just need to find N6, N7, and N8. So let's do a mass balance for these guys. So mass balance in the overall process of hydrogen atom will be inlet equals outlet. The inlet of hydrogen is of course N7, but there's 2 moles per mole, so I'm going to write 2, and 2 times the 0.9 that goes in N2, because they tell you it's the 90%, guys. I'm doing this. I'm doing all the hydrogen balances. So let's continue. N2 plus 4 times N4, because I have 4 moles in methanol, and I have 2 moles in N5, which is N5, where is it? N5 I think is, yeah, water. So this is water, this is methanol, and this is the hydrogen going out. And of course this is also hydrogen. So we got this nice expression. Let me, N7 equals 2 times 0.09 divided by 2 times n2 plus 4 divided by 2 and 4 plus 2 divided by 2 and 5. Substituting all the data, we know n2. Actually, let me just write everything. Times 12.4 plus 4 divided by 2, where's n4? I think it's 25.3 plus 2 divided by 2 and 5, which is almost nothing, but we need to account for it. And n7 I calculated 6.78 kilomole per hour. So that's the hydrogen we are feeding. That's cool. Now let's calculate mass balance, overall process, and calculate oxygen. So we say this, since there are atoms, inlets equals outlet. So we have N6 plus 2 times N8 equals N4 plus N5. Let's go here. You have N6 is CO and N8 is CO2. So that's why I counted double. And going out is methanol, which is 1, and water is also 1. Here it's only nitrogen and also CO and CO2. Let's go here. And for, I told you it was, this is the CO2, the CO. And for where is it? And for what's methanol? Yeah, this is methanol and this is water. I'm supposing all the CO2 and CO are recycled. CO here and CO2. Now solve for this, N6. So I got this equation. I don't know which number of equation is the next one. Okay, I think it's 11 was the last one. Yeah, let's call this equation number 12. And let's do another mass balance in the overall system. The only one left is carbon, so let's do it. N6. Oh, we have inlet equals outlet. The inlet is carbon CO and CO2, which is this. Just to let you know, CO and CO2. We need to account for 1 mole each. And the outlet is methanol, which is N4. It's only 1 also. So this turns into N6 plus N8 equals 25.3. And yeah, probably you're asking yourself, this is almost the same equations. And actually this value here and this value here are not that different. So the thing here is, yeah, there's going to be a little bit of assumptions, or well, not assumption, but a little bit mistakes, because we are accounting for a very small amount of this reaction. You can see because I ignored this, now I'm having problems. Probably this stream will be a very small stream. Solving. And 8 will be about this. And substituting number 13, you get N6 equals 25.22. So it's almost nothing, guys. I will say that N8 is almost 0. You don't need to feed nothing at all of CO2. They're not feeding that much CO2. The good thing is we are feeding a lot of carbon monoxide. So that's your analysis, guys. If you wanted to calculate the composition of this stream, or composition of the stream inlet, will be the CO, the hydrogen, and the CO2. Let's do it. The amount of CO is N6 divided by total amount Y of hydrogen, CO, This one is the amount of hydrogen, which is N7 and N8. Nt, in this case, it's N6 plus N8, sorry, N7 plus N8, which is N6, I have it as 25.22, N7, I don't think I have it, yeah, I think it's 61.70 plus this. Let me add this. 87. I got 87 kilomole in the mixture. So just substitute 25.2 divided by 87, 61.8 divided by 87, and almost nothing divided by 87. This one is 0.289, 71, and this is almost nothing. I will say it's, well, not zero, because if you say it's zero, it doesn't sound that nice, so I will say it's 0.0001. So you're done, guys. You're just finished. Of course, you will need to calculate the composition in here and in here, but that's not funny, and yeah, I think it's almost everything. The important composition are these, these, and these. So let's continue. The process is used to provide 237 kilomole per hour of methanol. Scale up the flow chart in part A and calculate the fresh feed in SCMH. Okay, they tell you also the reactor effluent and the actual volumetric flow rate, and assume ideal gas. So let's do it. Letter B, it's a scale for this amount of methanol per hour. So the scale factor, it's the new design, or N4 new design and N4 we design. So the new one is 237, and we just calculate N4. Where is it? Where's N4? We have it. N4 is this one, this guy, 25.3. So it's not that bad. We just need to multiply around 9, something around 9. I got this number. So yeah, this is the factor. Now let's process the volume in the feed of the reactor. We know that the total amount of moles in the reactor, it's, let me check the outlet. Where is it? Okay. Now the total feed, let me just check what they are asking us for. Scale up, okay. Fresh feed, oh, let's calculate first fresh feed, which is this, N6, N7, and N8. It's N6 plus N7 plus N8. That's the total amount of moles. Well, no, let me just clean up this. The total amount of moles in the feed, it's N6 plus N7 plus N8. And yeah, let me just review this. Okay. N6 and 7, I just calculated that, I think it was 87. Yeah, 87 kilomole. Now, let's go to the volume feed. Well, we need to scale that times 9.37. It's 815 kilomole per hour. And yeah, well, that's the amount. I'm going to use this, the volume, the amount of moles by NSBS, because they want it in standard conditions. That's pretty nice for me. I don't care. That's actually easier calculations. The amount is 22.4 cubic meters per kilomole. And you I calculated 18,260 cubic meters per hour. That's the volumetric feed. Good. That's the first one. The second one is fresh feed reactor effluent, which is the outlet, which is N2, 1, 2, 3, 4, 5 plus the 2 of nitrogen. So let me do that. Now in effluent, it's total amount of moles. I calculated 49.4. Hopefully you remember that. If not, let me just show you that I'm not lying. These guys. And 1, 2, 3, 4, 5, and the nitrogen. Don't forget the nitrogen. In this case, is a small amount of nitrogen, so it will not care if you forget it. But if it's a huge amount of nitrogen, you will have a huge problem because you will see the error very easily. So, what we need to scale up, so it's 19.37. You will get, let me see, it's 462 kilomoles per hour. So we are asked for the standard, so STP conditions. It's just the same thing we did before. 22.4 cubic meters per kilomole, and you get 9,950 standard cubic meters per hour. Now the second one is the real one, because that's good if you want to compare streams, but you probably want to know what to design for, not the standard conditions. So the real one, we need to add this N T divided by TS times PSP. So yep, total amount of NS, it's 995. Oh no, this is volume, sorry. Volume 9950 standard cubic meter per hour. Temperature, it's what was the temperature? 200 Celsius. So 200 plus 273 divided by 273, which is the standard, and the standard pressure is 1 atmosphere, or this amount of kilopascals, 101, and the pressure is, where is the pressure? Here, 4,925. 4,925 kilopascals. So do this, you get, which makes me a lot of more sense, because it's more, a little bit, 9,000, it's a lot if you compare it, but you're experiencing, or you're having a high pressure and high temperature, but this one is, I think, the strongest one. So when you have a high pressure, you have a way low, smaller flow. So yeah, this is letter B. I think we still need to do letter C. Use the rule of thumb for diatomic gases given in this page to test the ideal gas assumption at the reactor outlet. If the assumption is invalid, which is the value calculated in part B? In error. So I think they got this equation, this crazy one, that if you specific volume it's less than 20 liters per mole, it's not a good, it's not good. So we need to prove that it's bigger. Let me go here. So the volume we calculated is 355 cubic meters per hour, and the amount of moles is 400. Where is it? 3444. Where's the amount of moles? 462. 462 kilomoles per hour. Let me calculate that. 355 divided by 0. And you got cubic meters per kilomole, which is the same if we change it to liters per mole. So what I wanted to tell you guys is that our approximation is terribly wrong. It's not even near 20. It's not good, And why it's not good? Because of the same thing I told you guys. It's high pressure. Remember, ideal gas is not that good for high pressures. High temperature, yeah, it's okay. But for high pressure, no, not normally, no. So it's not a good approximation. And of course, if I were you, I will look in tables and look what will be the factor of compressibility, or look in other equations like the Birel equation, or Rubin equation, or SR equation, whatever. The thing here is that you cannot not use ideal gas. Yeah, we're done. Let me just make a small conclusion. We got this problem, which is methanol production. Very interesting that we got these two reactions having at the same time in equilibrium. So yeah, they give you a lot of data. And what we essentially did is calculate the extent of reaction, then do some mass balancing to get the molar composition. Now, having the molar composition here, we just substitute in the partial pressures, and with the partial pressures we substituted in Kp1 and Kp2. Once we got Kp1 and Kp2, which are Kp1 it's a function of epsilon1 and epsilon2, and K2 is also functional. These guys, we just solved for that in a software and we got these values. I think that's the most important part. Everything else is just substituting data. We got N1, N2, N3, N4, N5, and of course the inert gas nitrogen. We add all these, we got each one of them here, 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 and we got backwards, go to molar composition, substitute everything, and yeah, we got the first part, which is the reactor outlet. Now for the general process, we need to do a lot of mass balances in H and O and C, or hydrogen, oxygen, and carbon. You find all the inlet, and with the inlet you have everything. You got all the variables, which is N1 until N8. What else do you need? Oh well, they tell you to scale up is nothing but divide the new value and the old value. You got this factor. With this factor you calculate everything else, everything another time. For example, this total amount, I got this, and I needed to multiply to know the new value. With the new value, I got this new volumetric flow in the feed, and this volumetric flow in the reactor effluent. But this is standard conditions. What will happen if you do not use standard conditions, but the normal conditions of operation, which is 200 Celsius and 4,925 kilopascals? You will get this value. And they tell you to estimate, which if I were working, I will do this a lot to know if I'm near or how bad I am with my ideal gas assumption. And yes, as you can see, we are terribly wrong. We need it to be around 20, or at least near 20, and we are not even near 1, so that's not good approximation. And that's everything, guys. I think this problem is very, very complete. You have a lot of ideal gases, you got scale up, you got equilibrium, you got multiple equations. So if you did this and you understand it, I think you're set up for your exams and problems and homework. So good luck and see you in the other video.